So, hello everyone, my name is Subrata Samanta and I am from IIT Kanpur. So, I am your tutor for the physics subjects. So, in the previous class, I will discuss about the electric dipole in an uniform external electric field. Okay. So, and we calculate the potential energy of a dipole in an external field. So, let us summarize first this that what we got in the previous class. Potential energy of a dipole potential energy of a dipole in the presence of an external field. So, in the presence of an external field, there is U minus P E cos theta. So, if we write in the vector form, minus P vector dot E vector. Okay. So, this here the E vector is, so this E vector is the uniform electric field, uniform electric field vector, and P vector is the dipole moment vector, right. Dipole moment vector. Okay. What is the significance of this negative sign? Because this negative sign is means that, so when the dipole is parallel to the electric field, that means the potential energy minimum, right. So, when P is parallel to E, means that the dipole moment vector parallel to the electric field vector, in this case the potential energy is minus P, that means the minimum value U minimum, and the system becomes stable, because the system is stable when its potential energy is a minimum, right. So, this implies that the system stable, okay. And opposite case, when P is anti parallel to A, anti parallel to E vector, right, the electric field vector, then U P E plus P, right. So, this one is the maximum value, values of U, okay. So, then the system is unstable, right. So, system is unstable, okay. So, system is stable in this case when the dipole moment vector is parallel to electric field vector, and when it is anti parallel, then the system is unstable, okay. And the intermediate concept is torque, okay. So, is torque applied to the dipole, which enforce the rotate dipole and try to align to the electric field, okay, such that the potential energy is minimum and the system is stable. So, today I am going to discuss what happens when we place an dipole in a non-uniform electric field. So, dipole in a non-uniform electric field. In a non-uniform electric fields, electric field, non-uniform electric field. So, in the previous case, when we consider a dipole in an external uniform electric field, we see that only torque becomes non-zero and the force is 0, because the force on the positive charge is equal to the negative charge and the direction is different, okay. So, that is why the net force becomes 0. But today we will see that when the dipole placed in a non-uniform external fields, okay, the force becomes non-zero as well as torque. Okay. So, we calculate the net force on the dipole in this case. So, here the net force on the dipole net force on the dipole in this case. So, first draw a picture. Okay. So, let us consider a minus q charge and plus q charge, both have equal magnitudes because they form a dipole. Okay. And they placed on the x axis. So, this one is x axis, okay, and this one is a negative charge, this one is a positive charge, and this one is a center O, right. So, from the center, so the center at any point x, okay, and so let us say I cap unit vector, okay, x axis, and the force on the positive charge these directions, right, since the electric field vector in these directions. And this electric field vector in this case is not uniform, it depends on x, okay, the positions, and yeah. So, the force on the plus q charge A plus, okay, in these directions along the I cap, along the E vector, and on the negative charge is opposite to the E vector, right. So, in this direction, so F minus, and at this point the electric field E vector, right. So, at this point the electric field vector E at x plus A. So, let us say this one distance is A, okay, and this is the point x, okay, the plus q charge placed at a distance A from x, and this one is also A. So, at the position of plus q charge the electric field vector E x plus A, okay, depends on the distance, and this one is E x minus A, okay. So, this one let us say E plus and E minus, specifically specified the electric field at plus q charge at minus q charge. So, now we see that the electric field vector E plus, so electric field E vector plus at plus q differ from the electric field E minus, okay, at minus q charge, okay. So, E plus and E minus are differ, okay. So, that is why specify that the electric field is non-uniform, okay. So, now assume that the dipole to be very small and we expand the field. So, since that A is a small parameter, okay, small. So, here we consider that the dipole, the length of the dipole, the dipole 2A, okay, and it is small, okay, it's and small, okay, assume okay, and it's small. So, then we expand the electric field vector, okay, with respect to x, okay. So, the Taylor expansion, so E plus x plus A basically E the electric field vector at the point x plus A times d over dx. So, here we consider total derivative, since that the E only functions of x, okay. If E is a functions of x and y, okay, so then we use partial derivative instead of total derivative, okay. So, be careful, and E minus x minus A, which is approximately that E at point x minus A times d dx. Okay. So we consider only first term in the Taylor expansions, okay, and neglect the higher order term since that a is small. Okay. So we neglect higher order term in the Taylor expansions. Okay. Since that we assume that the length of the dipole is small. Okay. So then the force on the dipole becomes, so then the force on the dipole is Fe. So from Coulomb's law, what do you know, that the force on the dipole is basically the charge times the electric field at that point, right. So and we use the principle of superpositions. So the force on the plus q charge plus the force on the minus q charge, okay, just simply add algebraically. So and this one is a vector sum. So if the force on the plus q charge plus q times E plus vector, right, minus E minus vector, right. So the charge have same magnitude, okay, both charge, okay. So that's why we take our q outside, okay, and the difference in the electric field between 2 points. So now we use this thing that E plus, basically we put into these two expressions, okay. So we finally got that 2qa d over dx times, so in the directions I cap, right. So you consider the dipole is placed on the x axis, so that is why the I cap, okay. And if we write in terms of dipole moment, the dipole moment P magnitude 2qa, right. So the charge times the distance between the dipoles, right. So therefore the force becomes P times dE dx, okay, and I cap, okay. So here we see that the force basically the gradient of the electric field, right. So if the electric field is constant, right, so then the derivative becomes 0 and the force becomes 0, right. So when the electric field vary with the distance, okay, that means there is a non-zero gradient, okay. So then we get a force on the dipole, okay. So from here if we assume if E is constant, means that uniform, okay. So that means d dx 0, so it implies that force 0. So force on the dipole only non-zero when we place in an external non-uniform electric field. So in real life example, that a net force acting on the dipole is the attraction between a small piece of paper and a comb, okay. So so next I will discuss the next part of the charge density, okay. So charge density. So far we calculated the electric field when the charge configuration, means the discrete point charges, okay. So now I will going to be discuss the charge is distributed over a surface, okay, over a line, okay, not a discrete point charge but is distributed over a line, okay, and then over a surface and then over a volume, okay. Then how to calculate the electric field at some arbitrary point r in a space, okay. So first consider line charge density, okay. So line charge density. So if the charge is distributed over a line of length L, so if the charge is distributed over a line of length L, then we define a linear charge density lambda, then the linear charge density lambda is lambda as a functions of r equals to dq over dl. Okay. So, here we consider that the charge is distributed over a line. Okay. So, let us consider a rod and the charge is distributed over a rod. So, in this case the distribution functions may not be uniform. Okay. So, that means so that is why the linear charge density we define, that is a functions of r. Okay. It depends on the distance, okay, from the center of the rods, okay, or maybe from the ends of the rods. Okay. So, is a functions of r, that means may not be uniform. Okay. So, where the dimensions of lambda unit length, okay, so because the lambda, the dimension of lambda, dimension of charge by length, right. So, the unit just coulomb per meter. Okay. So, this one is the unit. So, now we calculate the total charge by integrating over length, right. So, the total charge is obtained by integrating over the entire length, right. Integrating lambda, okay, integrating lambda over entire length, okay, and I got q becomes integrating over line, okay, lambda as a functions of r times dl. Okay. So, this is the total charge q. So, again if the charge is uniformly distributed over the line, okay, so then the lambda becomes constant. So, in the next class we will calculate the total charge for a some specific charge distributions and then calculate electric field. Okay. So, thank you.